Imagine a world teeming with particles, most of which we never see. These particles, much smaller than atoms, are the building blocks of everything around us. One such particle, the muon, holds the key to unlocking some of the universe's deepest secrets. Muons are essentially heavier cousins of electrons, carrying the same negative charge but with a mass about 200 times greater. They are unstable particles, decaying into other particles very quickly, with an average lifetime of just 2.2 microseconds. This fleeting existence might make them seem insignificant, but it is precisely their ephemeral nature that makes them so valuable to physicists. By studying the way muons behave, we can glean insights into the fundamental laws of nature. To comprehend the significance of the Muon g-2 experiment, we must first delve into the world of particle physics. The Standard Model, developed in the 1970s, describes the fundamental particles of matter and the forces that govern their interactions. It has been incredibly successful in explaining a wide range of phenomena, from the behavior of subatomic particles to the evolution of the early universe. However, the Standard Model is not without its flaws. It fails to explain several observed phenomena, such as the existence of dark matter and dark energy, the masses of neutrinos, and the matter-antimatter asymmetry in the universe. These shortcomings suggest that the Standard Model is an incomplete theory, and that there is new physics waiting to be discovered beyond its current framework. This is where the Muon g-2 experiment comes in. The experiment aims to measure the muon's anomalous magnetic moment with unprecedented precision, looking for tiny deviations from the Standard Model prediction. Any discrepancy, however small, could provide crucial evidence for new particles or forces not accounted for in our current understanding of physics. When muons are placed in a magnetic field, their magnetic moments cause them to precess or wobble like spinning tops. The rate of this precession is directly proportional to the muon's g-factor. By carefully measuring this precession rate, physicists can determine the Muon g-2 with extraordinary accuracy. The g-factor, a fundamental property of particles, quantifies their magnetic behavior when subjected to an external magnetic field. In essence, it describes how strongly a particle couples to the magnetic field. For a point-like particle like the electron, classical physics predicts a g-factor of exactly 2. However, the quantum world, governed by the principles of quantum mechanics, introduces intriguing complexities. Quantum mechanics dictates that empty space is not truly empty, but rather teems with virtual particles, constantly popping in and out of existence. These ephemeral particles, although not directly observable, can interact with real particles, influencing their properties, including their g-factors. This quantum foam, as it is often called, modifies the g-factor from its classical value of 2, resulting in a small but measurable anomaly. The Standard Model of particle physics provides a framework for calculating the contributions of these virtual particles to the muon's g-factor. These calculations are incredibly complex, involving intricate Feynman diagrams that represent the various interactions between the muon and the virtual particles. Nevertheless, physicists have been able to calculate the Standard Model prediction for the Muon g-2 with remarkable precision. The experimental measurement of the Muon g-2, however, tells a slightly different story. While the measured value is very close to the Standard Model prediction, there is a persistent discrepancy, a tiny difference that refuses to disappear. This difference, though small, is statistically significant, suggesting that there might be more to the muon's magnetic moment than the Standard Model can explain. The Standard Model of particle physics, a triumph of 20th century physics, has been remarkably successful in explaining a vast array of phenomena in the subatomic world. It encompasses 3 of the 4 fundamental forces of nature: the electromagnetic force, the weak force, and the strong force, and describes the fundamental particles that make up all matter. Despite its successes, the Standard Model is not a complete theory. It fails to incorporate gravity, the 4th fundamental force, and leaves several observed phenomena unexplained. The existence of dark matter and dark energy, constituting the majority of the universe's mass-energy content, remains a mystery within the Standard Model framework. Furthermore, the Standard Model offers no explanation for the masses of neutrinos, neutral particles that interact very weakly with matter. Experiments have shown that neutrinos oscillate between different flavors, implying that they must have non-zero masses. This discovery contradicts the Standard Model, which assumes neutrinos are massless. The observed matter-antimatter asymmetry in the universe also poses a challenge to the Standard Model. According to the theory, matter and antimatter should have been created in equal amounts during the Big Bang. However, our universe is predominantly composed of matter, with very little antimatter observed. This asymmetry suggests that there are processes beyond the standard model that favor the production of matter over antimatter. These shortcomings and unexplained phenomena point to the limitations of the standard model and the need for a more complete theory of particle physics. The Muon g2 experiment represents a new era in particle physics, one characterized by precision measurements and the search for subtle hints of new physics beyond the standard model. The experiment builds upon decades of previous experiments, each pushing the boundaries of precision and refining our understanding of the muon's properties. The first Muon g2 experiment was conducted at CERN in the 1960s, followed by a series of increasingly precise experiments at Brookhaven National Laboratory in the United States. These experiments revealed a tantalizing discrepancy between the measured value of the Muon g2 and the standard model prediction, hinting at the existence of new particles or forces. The current iteration of the Muon g2 experiment, taking place at Fermilab in Illinois, aims to improve the precision of the previous measurements by a factor of 4. This increased precision is crucial for confirming or refuting the previous findings and for potentially uncovering even smaller deviations from the standard model prediction. The Muon g2 experiment is a monumental undertaking, requiring cutting-edge technology and the collaboration of hundreds of scientists from around the world. The experiment involves storing a beam of muons in a 50-foot diameter superconducting magnetic ring and precisely measuring their precession rate. The muons are produced by smashing a beam of protons into a target, creating a shower of particles, including muons. The muons are then carefully selected and steered into the storage ring, where they circulate at nearly the speed of light. The magnetic field in the ring is incredibly uniform, varying by less than 1 part in a million across the entire ring. This uniformity is essential for making precise measurements of the muon's precession rate. The Muon g2 experiment at Fermilab represents the culmination of decades of research and development in particle physics. It is a testament to human ingenuity and the unrelenting pursuit of understanding the universe at its most fundamental level. The experiment involves a complex interplay of cutting-edge technologies, from particle accelerators to superconducting magnets to ultra-precise detectors. At the heart of the experiment lies a 50-foot diameter superconducting magnetic ring meticulously crafted to maintain an incredibly uniform magnetic field. This ring, a marvel of engineering, stores a beam of muons, guiding them along a circular path at nearly the speed of light. These muons, produced by smashing a beam of protons into a target, are carefully selected and injected into the ring. As the muons circulate within the ring, their magnetic moments, interacting with the uniform magnetic field, cause them to precess or wobble like tiny spinning tops. The rate of this precession is directly proportional to the muon's G factor, the quantity that the experiment aims to measure with unprecedented accuracy. To capture the subtle dance of the precessing muons, the experiment employs an array of highly sensitive detectors strategically positioned around the ring. These detectors, designed to measure the energy and arrival time of decay products from the muons, provide the crucial data needed to reconstruct the muon's precession frequency. The success of the Muon g2 experiment hinges on minimizing uncertainties and controlling systematic errors. The experimenters have taken extraordinary measures to ensure the stability and uniformity of the magnetic field, the precise injection and storage of the muon beam, and the accurate measurement of the muon precession frequency. The data analysis, a Herculean task in itself, involves sifting through a vast amount of data to extract the subtle signal of the Muon g2. In the realm of particle physics, where the pursuit of precision reigns supreme, the Muon g2 experiment stands as a shining example of pushing the boundaries of measurement accuracy. The experiment's goal of measuring the muon's anomalous magnetic moment to an unprecedented level of precision demands meticulous attention to detail and an unwavering commitment to minimizing uncertainties. The experimenters have implemented a multi-pronged approach to achieve this extraordinary level of precision. One crucial aspect involves maintaining an incredibly stable and uniform magnetic field within the muon storage ring. Even minute fluctuations in the magnetic field can introduce significant errors in the measurement of the muon precession frequency. To mitigate these fluctuations, the experiment employs a sophisticated system of superconducting magnets and magnetic shielding. The superconducting magnets, cooled to extremely low temperatures, generate the strong and uniform magnetic field required for the experiment. The magnetic shielding, on the other hand, protects the muons from stray magnetic fields emanating from the environment, ensuring the purity of the magnetic field within the ring. Another critical aspect of achieving high precision lies in accurately measuring the muon precession frequency. The experiment uses a technique called blind analysis to eliminate potential biases in the measurement process. In blind analysis, the data is analyzed without knowing the actual value of the muon g2, preventing the analysts from subconsciously influencing the results. Furthermore, the experimenters have developed sophisticated algorithms and statistical techniques to account for various sources of systematic errors. These errors, arising from imperfections in the experimental apparatus or limitations in our understanding of the underlying physics, can skew the measurement results. By carefully identifying and quantifying these errors, the experimenters can minimize their impact on the final result. The Muon g2 experiment, with its quest for precision and its potential to unveil new physics beyond the standard model, has far-reaching implications for our understanding of the universe. A confirmed discrepancy between the measured value of the Muon g2 and the standard model prediction would be a groundbreaking discovery, opening up new avenues of exploration in particle physics. One of the most exciting possibilities is the existence of new particles that interact with muons but have so far escaped detection. These hypothetical particles, if they exist, could contribute to the muon's anomalous magnetic moment, explaining the observed discrepancy from the standard model prediction. The nature and properties of these new particles would provide valuable insights into the fundamental building blocks of matter and the forces that govern their interactions. Another intriguing possibility is the existence of new forces beyond the four known fundamental forces of nature. These new forces, if they exist, could also interact with muons, modifying their magnetic moment. The discovery of new forces would revolutionize our understanding of the universe, potentially leading to a unified theory that encompasses all known forces. The Muon g2 experiment could also shed light on the nature of dark matter, one of the most profound mysteries in modern physics. Dark matter, which interacts gravitationally but not electromagnetically, constitutes the majority of the universe's mass. While the standard model does not provide a suitable candidate for dark matter, new particles or forces beyond the standard model could potentially explain its existence. The implications of the Muon g2 experiment extend far beyond the realm of particle physics. The discovery of new particles, forces, or phenomena could have profound implications for our understanding of cosmology, astrophysics, and the evolution of the universe. It could even lead to technological advancements that benefit humanity in unforeseen ways. The Muon g2 experiment stands as a beacon, illuminating the path forward for particle physics in the 21st century. As we delve deeper into the subatomic world, the pursuit of precision measurements and the search for subtle hints of new physics will continue to guide our exploration. The experiment's legacy will extend far beyond its immediate results, inspiring new generations of physicists and shaping the future of the field. The quest to understand the muon's anomalous magnetic moment is far from over. The Muon g2 experiment at Fermilab is expected to collect data for several more years, further improving the precision of the measurement. The experimental collaboration is also exploring ways to upgrade the experiment, potentially pushing the precision to even greater heights. Beyond the Muon g2 experiment, other experiments around the world are also probing the frontiers of particle physics, searching for signs of new physics beyond the standard model. These experiments employ a variety of approaches, from smashing particles together at ever higher energies, to searching for rare particle decays, to studying the properties of neutrinos. The theoretical landscape of particle physics is also evolving rapidly, with new ideas and models emerging to explain the shortcomings of the standard model and address the mysteries of the universe. These theoretical developments, in conjunction with experimental results, will guide the future direction of the field. The future of particle physics is bright, fueled by a combination of experimental ingenuity, theoretical innovation, and an unquenchable thirst for knowledge. As we continue to explore the subatomic world, we can expect more surprises, more mysteries, and ultimately, a deeper understanding of the universe we inhabit. The Muon g2 experiment, with its focus on a seemingly esoteric property of a subatomic particle, exemplifies the interconnectedness of the cosmos. The quest to understand the muon's anomalous magnetic moment is not merely an academic exercise, but rather a profound journey into the heart of the universe, a journey that could ultimately unravel some of its deepest secrets. The experiment's potential to reveal new particles, forces, or phenomena beyond the standard model has far-reaching implications for our understanding of the universe's origin, evolution, and ultimate fate. It could provide crucial insights into the nature of dark matter and dark energy, the driving forces behind the universe's expansion and structure formation. Furthermore, the Muon g-2 experiment could shed light on the fundamental laws of physics, the very fabric of reality. The discovery of new particles or forces would necessitate a revision or extension of our current understanding of the universe, potentially leading to a unified theory that encompasses all known forces and particles. The pursuit of knowledge, exemplified by the Muon g-2 experiment, is a testament to human curiosity and our innate desire to comprehend the world around us. It is this insatiable curiosity that has driven us to explore the farthest reaches of space, to delve into the intricacies of the human brain, and to unravel the mysteries of the subatomic world. As we continue to push the boundaries of knowledge, we can expect more surprises, more challenges, and ultimately, a deeper appreciation for the vastness and complexity of the cosmos. The Muon g-2 experiment, with its potential to unveil new physics and deepen our understanding of the universe, stands as a shining example of the power of human ingenuity and the enduring quest to unravel the secrets of the cosmos.